Glad I can share it with you so you can see it as well as I. And let me just add a new page. Okay. Got a little bit of background noise on my end, but I think it'll pass. Anyway, everyone can see my screen, I hope.
Yeah.
Great. Okay. Well, let me start off with a new chapter. We'll get to other things later. I guess if you weren't here last time, I will mention we did set up an exam date, which is 2 weeks from today, which is February 4th. Whoops, March 4th. Sorry about that. And more to say on that as time goes on. And today we are going into chapter 2. So chapter 2 is entitled Linear Transformations and Matrices. And at first we deal with linear transformations. And so where we're at, let me see if I can give a little summary. I have the basics of vector spaces and dimension and linearly independence and linear and spanning and generating spaces and subspaces, and that's the material we've been covering. So the new topic for today particularly is called transformations. And it turns out transformations are very closely related to matrices. So this chapter deals with both, but at first it just talks about transformations by themselves. And later as we progress in the chapter, we talk more about the connection with matrices. Okay, so what we're looking at here is a function. So a transformation is a function usually called T for transformation from one vector to another, one vector space to another. So let me see if I can, use the notation your book is using. So it's a function T from from V to W, I guess. Yes, that's their notation. Where V and W are vector spaces. Okay, now V and W could be different vector spaces, or they could be the same. And we all know what a function is from Math 3100. Function for everything in the domain assigns one value in the codomain. And there are properties of functions, which might be good to review. So you might want to review, I'll put it in parentheses here, review the definition of functions. Say given in Math 3100. In particular, you may want to review concepts such as one-to-one, which is also sometimes read this way, and onto, we'll go over them a little bit when the time comes up, but it would be great if you already did some preliminary reading so you know what those concepts are about. These things have other names. This is called, I have to think about it. One of them is injection. And what is the other one? Surjection. So surjection is this one. That's a French word actually, used for synonymously to onto, and one-to-one is called an injection. You don't have to know all these terms. If you knew one-to-one and onto, that probably would be enough. But surjection just is another way of referring to onto, and injection another way to refer to one-to-one. And if you have both, if you have a function, if a function is both one-to-one and onto, or injective and surjective, then it's called different things. So something that's one-to-one and onto is usually called a one-to-one correspondence. And something, so this is slightly confusing, because if you're both one-to-one and onto, then the function is called a one-to-one correspondence. That's when the word correspondence appears. On the other hand, if a function is injective and surjective, then it's called a bijection. So these are all terms that you would be well advised to refresh yourself on with regard to functions. Some of that refreshment or some of that drawing on your memory there will come about naturally. Now, so this is sort of, all of this stuff I would say is parenthetical information of how to do your review. Let's go back to the first sentence of transformation T from V to W. I guess I should have said is a function where W and V are vector spaces. This is really the start of the parentheses. So all of this would be parenthetical material, starting right here, maybe. But there's more to a transformation than what I've said. So let's continue the definition. And this is on page 65. It has to have two properties. So the two properties that you need to call it a transformation, and actually they call it a linear transformation, which I sort of like. So let me go back, is a linear transformation. T from V to W is a function where V and W are vector spaces, and these two properties hold. The first property, called A in your book, is two properties hold where X and Y are vectors in V, and C is a scalar in our field, which we've been using mostly to be R. And two properties hold where X and Y are vectors in V, and this holds, and the two properties are A, if you want to take the transformation of the sum of these two vectors, you can do it by taking the transformation of the first one and adding it to the transformation of the second one. And this would have to really hold for all X and Y. So there's a quantifier here where X and Y are the two vectors in V.
Excuse me, Professor.
Yeah.
I'm so sorry. I was having some internet trouble. Is there any way I can get permission to record?
No problem at all.
Thank you.
Just hold on a second. Let me just take a second out and do that. So that's not a big deal. Except, I'm sorry. Who are you?
It's Chris Traub.
Okay, thank you.
Thank you so much.
Yeah. I think you have it. Is there anyone else who needs permission to record since I'm here anyway? It's a good time for me to do it. Looking to just see if there's any other familiar names here. Okay, I don't see anyone else. So let me just go back. Okay, so this property I call linearity. Let's see what they call. They didn't call it anything. So I would call this the linearity property. And B is you take any vector and you multiply it by a scalar. You get the same thing if you take C times the transformation of X. And this also holds for all X and V. So these are properties. This would be property, I don't know what to call it again. I guess it would be a property of scalar multiplication. So what it really says, if you take a vector, scalar multiply it, and then transform it, you get the same vector as if you first transformed it and then scalar multiplied. So I'll just call it the scalar multiplication property. Okay. Now, so I'm looking, this is on page 65. So if you're trying to follow along with what I'm doing, it's in the new chapter 2. Underneath this definition, they talk about what the field could be. It could be rational numbers, typically, again, it would be the reals. They call such a transformation linear. And then they say the reader should verify the following properties of a function t going from v to w. So in this context, again, if you go back to Math 3100, this way of writing it, let me see. Well, actually, I haven't written it the way that I would like to write it. So instead of saying t from v to w as a function, the notation that most books these days use for a function is the following. So they would show t colon, and then what follows is the domain, v in this case, and then an arrow going into w. Now let me see if your book uses that at all. They do. So they do that in their definition. So this is what we're talking about. But this notation doesn't tell you everything you need to know. It tells you the domain. It tells you the codomain. It tells you that this is a function. So what does that mean? For every vector in here, there's only one value assigned over there. But what it doesn't tell you is that t is linear. T is linear, or linearity. I think together to these would be called the linearity properties, both of them. So if you want t to be a linear function, you need both a and b to hold. And they both have quantifiers, right? So they hold for all x's and all y's and all c's. I guess that should have been stated here too. Okay. So some questions naturally arise whenever you're define something like this. It would not be nice to see examples. We will do examples very shortly, but I'm following a little bit the order your book is going. So what they say next is the reader should verify the following properties of such a linear function. Well, let me see. I'm beginning to wonder if this notation in this book means more than what it does in most books. What I already just said is this means you're a function going from v to w. But perhaps in this book, this also means that you're a linear function. Why? Because that seems to be, we call a function, this a linear function if these properties hold. And they just call t linear. So it's not entirely clear. They may just be using this notation to mean all of this stuff and the linearity properties as well. Linearity properties. We'll have to go a little further and see how they're using the term. But what else are they saying that holds? So here's an exercise for the reader, which means you guys. Exercise for the reader. So if t is linear, then t of the zero vector is the zero vector. So let's write down these things since you're being asked to show that they're true. This is number one. So if t is linear, then t of 0 equals 0. However, be careful. These zeros are vectors, and this one here, so be careful. let me go even so far as to label them 0, 1 and 0, 2. 0, 1 is the 0 vector in V. And 0, 2 is the 0 vector in W. And they may not be the same. So you have to be conscious of that. So if you're going, for example, from a one-dimensional vector space to a two-dimensional vector space, then, well, even better, say this was 2 to 3, the 0 in the two-dimensional, if V was, for instance, R2, then 0, 1 would be the vector 0, 0. And if, for instance, W, whoops, yes. I'll make sure I know what I'm doing here. Yeah, W. If W were R3, then 0, 2 would be 0, 0, 0. So what we're saying is that the function takes the 0 vector in V and assigns to it the 0 vector in W. Now, they don't write 0, 1 and 0, 2. So they're putting the burden of understanding that on you. So I've written it this way, but again, the book is just writing it this way, which is what? Ambiguous, not clear, because one could get confused. You could look at both of these zeros and think they're the same 0 vector. They may be the same 0 vector. If W and V were both R2, then they would both be this 0 vector. But if V and W are these, then we're talking about different 0. Let's look at the other properties. Property 2, T is linear if and only if we can write this. And again, linear is just short for a linear transformation. If and only if T of they write it this way, which is not the way I would write it, but let me give it the way they give it first. Okay. What they're saying basically is they're connecting both of these things together. This is what we normally think of a linear property, which says what I already said. You can do the sum first and then transform it, or you could transform it first and then do the sum. The order of the operations doesn't matter for a linear transformation. And then this property where you can factor out the scalar has been defined separately. And this is simply combining both. Now, for me, what I probably would have written, instead of writing this, I probably would have written something like this. AX plus BY is ATX plus BTY. And I would have written for all XY in V and for all A and B and F. Because this is a little more general than what they're writing. So what I'm suggesting is you take something that looks like this, which we've called a linear combination of x and y, where a and b are the scalar coefficients. If you're taking the linear transform of that sum, you can take the sum of those individual linear transformations, and then you can factor out the scalars. Anyway, I'm not sure why they've written it this way. I probably would have written it this way. In either case, you need to know that both of these hold whenever you have the linearity properties. Any questions on properties 1 and 2 so far? I haven't proved them, I'm just stating them. Maybe I'll prove 1 or 2, we'll see. 3. They should be easy, relatively straightforward. If t is linear, so if t is linear is the assumption throughout this. So if t is linear, or that's just short for linear transformation, then what are they saying? Then they're saying, well, they're saying this. The transformation of the difference of two vectors would be the transformation of the first vector minus the transformation of the second. And this would hold for all x and y. See, that would come out of what I just said, because I would take a to be 1 and I would take b to be -1. And then you would pretty much immediately get this from what I said above. And the last property they want you to realize holding is more complicated. But okay, this one is really a generalization of what came earlier, and it includes what I said and even more. So let's look at this. If t is linear, then t of a finite sum of scalars ai, vectors xi, where I goes from 1 to n. It should be, can be written as the summation of the ai t of xi, I going from 1 to n. Yeah. And again, this would have to hold not just for any, well, not just for a particular set of vectors, but for every x1, x2, up to xn, and for all scalars, a1, a2, up to an. Okay. Well, for some reason, they did this with just 2 terms first. This is the generalization of what I said up here. So I said if you had just a linear combination of 2 vectors, it would be a times t of x plus b times t of y. And they're saying if you had more than 2, it would look like this. So don't be put off by the summation notation. Let's just make sure we understand what it says. It's really saying that if you've got something that looks like a1 x1 plus a2 x2, you keep on adding it till you get to an xn. That's the same as a1 t of x1 plus a2t of x2 plus keep on adding until you get to the end of the line, an t of xn. So this is written longhand, and this is written the same way. This is the same this property here is the same as this property here. This is written using summation notation, and this is written out longhand. Okay. This is an exercise, and we actually get the number. Let's take a look and make sure it's correct. We call it exercise 7. Fine. So that's homework. Exercise 7. Back where? Back on page 75. There'll be more. Okay. So the obvious question that comes up is, give an example. So let me give an example. Let's let the vector space be the real line, and let W also be the real line. Okay. And what we're asking is, what would be a linear function t that goes from R to R? Now, first of all, R is thought to be a vector space where the real numbers are just thought to be the vectors. And scalar multiplication, well, this R is a little confusing because the vectors look like scalars, right? If we take the vector field F to also be R, then the scalars are all real numbers and the vectors are real numbers. So this is a very simple example, but that's by intent. I want a simple example, but it may be so simple you have to think about what are the vector operations. So what would be vector addition? Vector addition would be just what you think it is. It's the addition of two real numbers. What would be scalar multiplication? Well, the only multiplication that we've defined on R really would be the multiplication of two numbers. So vector addition is just normal addition. Scalar multiplication is just normal multiplication. And the vectors and the scalars in this case turn out to be the same. You can think of it this way. You can think of the vectors as just having one component. And so in that sense, the vectors just have one tuple, and that tuple could be thought of as just the number itself. Okay, so then this looks very familiar. What does this look like? Well, this looks like the setting for Calc 1, 2, Calc 2. This is the setting for Calculus 1. And 2, because that's what you do in the first 2 semesters of calculus. You basically study functions that are going from R to R. You learn how to differentiate them, you learn how to integrate them, and so forth. Okay. Higher dimension stuff is usually covered in Calc 3, by the way. That's where vectors are normally first seen, or vectors that have more than one component, I suppose. Okay, so now the question is, so here's my question. What do linear functions as defined above, well, maybe we should say linear transformations, sorry. So we're not using linear functions, we're using the word transformation because it has more properties. What do linear transformations as defined above look like? Okay, well, let me make that an actual question for the class. If you're going from R to R, what do you think the linear transformations look like? If you don't know, guess. Okay. Oh, come on.
Maybe one where the transformation doesn't do anything. So T of X equals X.
Okay, so you're giving me an example. So you're thinking T of X equals X. And I'm sorry, was that Alberto?
John.
That was John. Thank you. So John says maybe T of X equals X. So that would be an example. I'm sort of asking for what they all look like. But what does this look like? Let's go with John's example. T of X equals X is sort of from R to R would be what? Just the straight line. This is R, this is R. And if anything on here, X is just given the same value, X. I think what you've just given me is the straight line. So, okay, let's go with what John has given us. Is that a linear transformation on the vector space going from R to R? Well, I mean, one answer is it's a line. So it's a line linear, but that sort of sounds funny. It's like saying is an orange orange. Yeah, an orange is orange and the line is linear. Okay. So, but is it a linear transformation? Well, what we got to check are these properties. That's what definitions are for, right? So there's no problem taking V and W to be R. Those are vector spaces themselves where vector addition is addition of real numbers and vector multiplication is multiplication of real numbers. All the vector assumptions will be true. So John has defined for us an example. And is this property here true? So basically, linear transformation is a function that has these two facts. So let's check them. Okay, so T is defined this way for all X and R. So the first property says if you had two real numbers, then what would T do to them? Well, I think it's just going to give you back the same real number, right? Okay. And what we're trying to see is, does property one hold, or property A hold over here? Well, he already told us T of X is X. So this is this. And if you're on the line, Y is some other number here. And then you get Y wherever it is. That's also on the line. So what if I just checked? I've just checked property A. So John, so far you're looking pretty good. Property A holds. But what else should I have said? Well, it would hold no matter what X and Y were, right? But no matter what X and Y are, the function you gave me just keeps the value the same. So X would be T of X and Y would be T of Y. So this would hold for every X and Y in R. That's property A. So far, so good. What else? Well, we got to check the second condition, property B. Property B is this guy. So if you took some scalar And again, this is a little confusing because the scalars are really the same as the vectors because, well, we're just in R1. If you took the transformation of CX, what would you get? Well, according to John, he basically gave me the identity function, right? Whatever X is just gives you back whatever X is. So T of CX would be what? CX. Because of how we define this, we're on the line Y equals X. And what else? What do we got to check? Well, what we got to check is this equal to what? CTX? Question mark? Because that's what property B is about. It says if you take the transformation of a scalar times a vector, you get the same as the scalar multiplied by T of X. The T of X is X again, according to John. So since that equals that and C is the same, I'd say this is true. So property B holds. Now, what should I have said? Got to check this for all C and all X and R. But that's true still. So good job, John. This is a linear transformation. Does it make some sense? Yeah, a line you might expect to be linear. You may have the same base in the word, line, lin. Okay, so this is a linear transformation. Is it the only one? Can someone come up with another one other than John, maybe? John's done the heavy lifting so far.
Can we do a T of X equals square?
Say it again, please.
Can we try T of X equals h squared or h cubed?
Okay, and who's that speaking, please?
This is one.
Juan. Okay. So Juan is suggesting why not, what I'm hearing from Juan, T of X equals what, X squared, for example?
Yeah.
Okay. Nice choice. It's a little more complicated than T of X equals X. T of X equals X is just like Y equals X. So that was a straight line. This is a parabola. Okay, so what are we asking? Is a parabola a linear transformation? That's what we're sort of asking here. We're following Juan's thought. Well, let's just go through the properties. So there's two properties, property A and B. Let's go through the first one. Property A would say what? According to what we just defined, is T of X plus Y equal to Tx plus Ty. That's called the linearity property. Well, let's check it out. T of X is X squared according to Juan. So T of Y would also be what? Y squared. And we can draw the picture. The picture would be a parabola, right? A standard parabola here, XY coordinate system. Y equal X squared. Okay, so on the right side, you have xt, according to Juan's suggestion, you have T of X equals X squared. T of Y would be the same. And what would this be? Well, according to Juan's function, you take whatever you're given and you square it. And so now that's the question. Does that property hold? And yeah, I heard the right answer. No, it doesn't. Why not? Because if you square the sum, you get X squared plus 2xy plus Y squared. And does that equal X squared plus Y squared? No. Why not? Because if this were true, then the X squares would cancel and the Y squares would cancel. And you'd have 2xy equaling 0. And that wouldn't hold for all X and Y, right? Because this has to hold for all X and Y. That's part of the property A, right? For all X and Y and R. And it doesn't, because if I just let X and Y be 1, it gives me 2 times 1 times 1 equals 0, which gives me 2 equals 0, which is not true. Now somebody could say, well, that's just for X and Y being 1. Suppose you pick X to be 0 or something. Well, yeah, but this property is supposed to hold no matter what I pick X and Y equal. So if I find one X and Y that makes it work or fail rather, then my job is done. We've shown it's not linear. And in a way, that makes sense. Because if you think of linear as being a line, think of lines, we're sort of asking, is a parabola a line? And the answer is no, it's a curve. I think you can see one for the same reason T of X being X cubed won't work either. So thank you for your answer. Not so much because it was what I was looking for, but it's good to understand what we're dealing with. We're looking at things that are linear. So far, we've got one example, thanks to John. And we've got one now, thanks to Juan, that's not linear because it doesn't have the linearity property. The linear property is this thing right in here. So we need a function that does that. And this one won't. So we now have, just in the calculus setting, the XY axis, we have functions that are linear functions and we have functions that are not. Let me go back to my original question. Are there other linear functions than the one that John gave me? If so, could someone please give me it? Or if you're not sure, just give me another linear function.
Since we're looking at like linear functions, could we do like Tx equals x plus 2?
Okay.
Or,
And this is who's speaking?
that was Brett.
Brett, is that 1T or 2?
1t.
Okay. So Tx, I heard, I'm sorry, was it 2x plus something? I say it again.
I just did x plus 2.
Oh, x plus 2. Cool. Okay. So we're still in we're in familiar land, right? We're not up in some 5-dimensional vector space. We're in R going to R. I mean, that should be our home court, right? R to R is what you spent calculus days doing. So here's a function going from R to R. This looks like a line, right? If we were to graph it, let's take graphs, because we've been graphing these things, why not? We have an XY coordinate system. This is the line, in fact, it's just like John's. It's a line with slope 1 that has a y-intercept of 2, right? So the y-intercept, if this is the y-axis, this is 1 and this is 2, it would be a line that goes like that. Keeps going. It's going that way, it keeps going that way. Okay. What do you think? Well, okay, there's an advantage over ones. What's the advantage over ones? Suggestion.
This one is actually linear.
Yeah, it's actually a line. Yes, it's linear. Yes, okay. So if linear means line, this is linear. So maybe it is a linear transformation. But you can't always tell from a picture. And we do have a defining properties of what it means to be linear. So let's use them. What it means to be linear are these two properties. If something satisfies these two, then we're home. And if they don't, then it's not a linear transformation. Okay, so let's try it again. So let's try property A. I mean, that seems, we're just going in the order. Property A again. Property A. And what did that say? T of x plus y has to be equal to what? T of x plus ty? Okay. So Brett gave us T of x. T of x is just this guy. That looks like y equals mx plus b, right? Where m is 1 and b is 2. So that's T of x. What would T of y be? Well, I assume it'll be the same kind of deal. If you put the y where the x is. Okay, so we know what this is. We know what this is. What would T of x plus y be? Well, I again would assume you just put the x plus y where the x is. Plus 2, right? Everyone see what I'm doing? I'm taking the function that Brett gave me, which was for any x in R. This is true for all. This is true for all x in R. X is thought of as my vector. You just add 2 to it. So Tx would be x plus 2, Ty would be y plus 2, T of x plus y would be x plus y plus 2. Okay, now what? Take that and put it into here and see if it works. If it does, at least we're rolling, we have property A. If it doesn't, well, since we need both A and B, then the answer would be negative. So if you put in T of x plus y, that's this one, x plus y plus 2. Is it equal to Tx? Well, Tx is x plus 2. I'm using all this, right? And Ty is y plus 2. Okay. Well, does this hold? Well, there's an x on both sides. You can cancel that. There's a y on both sides. You can cancel that. And there's a 2 on both sides. You can cancel one of those on each side. On this side, there'll be 0 left. On this side, there'll be 2. Well, that's no good. For the linearity property to hold, you have to believe that 0 equals 2. And I hope none of you believe that. So what does it mean? And this is supposed to hold for every x and every y, but I don't think it matters what x or y you put in, you're going to get a falsehood. In other words, this is not true. So what does it mean? Property A does not hold. That could be a surprise. By the way, should we go ahead and check property B? No. What's the point? If we're trying to find a linear transformation, we need A and B to hold. And if A doesn't hold, you know, nothing more would be found by B holding or not. You need them both, and A doesn't hold. Okay, so this is a mild surprise. Why? This is a line. So a line may not be a linear transformation. But then again, there's John's, and this is a line, and that is a linear transformation.
Do they both have to be lines that go through the 0 vector? Because x plus 2 doesn't go through the 0 vector.
Ah, very good. Who is that? Is that
Emma.
Emma? Thank you, Emma.
So
Yeah.
like example would be x to 2x.
Yes, yes, I love it. Okay, let's put down hers. So Emma's suggestion is adding to the discussion. Why not try Tx to be what I just heard was 2x, right?
Yeah.
And 2x is still a line, but it's a line that goes through the origin. That's what she was saying. And of course, it's a line that has twice the slope of the initial one due to John, I guess. Yeah, keep the name straight here. So this would be the line y equals 2x. So Emma's suggestion is what? Stick with lines, but make sure they go through the origin. How did she come to that? Well, I can guess from Brett's suggestion, it was a line that didn't go through the origin and it didn't work. So she started probably thinking, how is this line different than this one? And one obvious answer to that question is, well, this one ran through the origin and this one did not. So that's a really good thought. Moreover, if you look at the exercise, look at condition 1. If t is linear, then t of 0 has to be 0. What is that really saying? That's saying the 0 vector has to go to the 0 vector. But the 0 vector in this case is just the 0 number. So that would say that t of x has to be 0. I'm sorry, t of 0 would have to be 0. And that confirms what Emma said. That confirms Emma's guess. Well, let's go through it. Let's double check. So property A. We have to check if t of x plus y equals t of x plus t of y. And that has to be true for all x and y in R. But with Emma's suggestion, t of x was 2x, t of y would be 2y. And t of x plus y would also be what, 2x plus y? Because whatever you give t, it just multiplies it by 2. So if you put that in here, you get 2x plus y, parentheses like that. And over on the right side, you get 2x, and over here you get 2y. And that's true. Why? That's the distributive property. If you distribute the 2 through the sum, you get 2x plus 2y. And that's true no matter what x and y are. So this looks better. This is true. It's a recognizable property of R. R is just the distributive property. Okay, but that's just property A. What's property B? Property B was t of cx had to be what? Ctx. And by the way, this had to hold for all x, y, and z in R. And it does because the distributive property holds for all real numbers, right? So the second property, property B, would be this guy. And, well, I guess the one that Emma gave us out first, tx is 2x. So on the right side, you have c times 2x. What about on the left side? Well, whatever you give it, you just multiply it by 2. So that's 2 times cx. Are they equal? Sure. Why? Associative property? No, not even associative. Take it back. Commutative property, right? You're commuting the order of these two. Associative property has to do with grouping and which comes first. This has to do with the order change. 2 times c is on this side, c times 2 is on this side, but they're the same. And so this whole thing is the same, and that would hold for all x in R and for all c in R. So good news. 2x, Emma, you're correct, is a linear transformation. Okay, so let's put all this together. John gave us the identity function for the line y equal x. That worked. One tried the parabola, but doesn't satisfy property A, the linearity property. So that was not linear. Brett came back with another line, but it didn't go through the origin. And that cost us the linearity property because we checked it and it didn't work. Emma noticed that and came back just multiplying x by 2. So that's another line, but it's through the origin this time, and it seems to work. So let me wrap this up because we've spent a little more time on this than I might, but I still think it's useful. But do we have them all? Well, sort of. What I'm suggesting if it's going to be a linear transformation, it should be a line to begin with. So linear transformations should be lines. But it turns out, but not all lines work. So which lines? Well, let's just generalize what Emma did. Lines that look like y equal mx. In other words, the y-intercept has to be 0, or in other words, the line has to run through the origin. Lines passing through the origin. I'll let you verify that any line like that works. It's pretty much what we did above up here. Instead of 2, as Emma had, you would have mcx equal what? cmx. So there's the verification. And I'm even going further. If W and U are the real line, then the only linear transformations are these guys. Now, I didn't prove that. I mean, somebody could say, how do you know there's not some other squirrely, function that's linear as well? But I'm just going to tell you that this is basically it. Now, lines through the origin, does that ring a bell anywhere? Have we talked about those already?
Subspaces.
Yeah, lines through the origin in R2 are subspaces. So it looks like, how many subspaces are there? Infinite many, right? I mean, M could be 1, 2, 3, 1/2, square root of 2, a lot of things M could be. So there's a lot of linear transformations in R1. Anything that looks like this will work. And the correspondence with subspaces in R2 makes you wonder how things would work if you made the vectors, well, suppose you made the linear transformation go from R2 to R2 now. Well, we just did R2. Let's see, what did we do? We did R1 to R1. So if we went from R2 to R2, which is the next step up, right? Now, I guess we could go from R2 to R1 because the vector spaces don't have to be the same. Or maybe I'm trying to think what's the next easiest step. Suppose T went from R2 to R1. Yeah, that might be the next easiest step. Why? Because that's what you did in Calc 3, right? There, when you took something in the plane and you defined another function from it, you use their f, and it went from R2 to R1. And I know I'm out of time, but I'll just finish this thought. But this is like what? The thing in here you called xy, and the thing that came out you called z. And what does this look like? Calc 3 or math 215, or I'm sorry, 2140 now. So maybe that's the next natural thing to do. Why? Because that's the next one you did in calc. All of first year calc was going from R1 to R1. Third semester calc, or calc 3, went from R2 to R1. So let's do that one, because it looks like this. Okay. But how do you draw those things? You draw them. R2 is usually drawn as the XY coordinate system, and that's the domain, and where you're going into, the codomain is what? The z-axis. So what do functions that look like this look like? Surfaces? Time needs time to stop, I think. Surfaces. Okay. And now here's a homework problem. What functions like this are linear transformations? What f functions are linear transformations? Homework. So we have a couple homework problems so far. Homework problem number 1 was exercise 7, which was to verify these 4 properties. Homework problem 2, which sort of is an outgrowth of what we just did in class, is if we're going from R2 to R1, and we're looking at functions that look like z as a function of x and y, which of those are linear transformations? I'm not asking you to prove it so much, I'm asking you to discover your answer, just in the way we discover the answer here from R1 to R1. Okay, let me give you a couple more problems, call it a day here. So we got somewhere. Let's see where I want to be. Try to do number 9 as well. We already have 7, now 9 from the book, or from page 75. Let me see, I don't think. Really can't give you 2 through 6 yet. Let me tack on 11. That one I can do. 7, 9, and 11, and the exercise that is given here. So 4 problems. So class is over, and I will take a little water, take a 30-second break to transition to problems. But I'm happy to work problems, past problems, current problems, questions from today's lecture, or anything in the past. So I'll see you in about 20 or 30 seconds if you're hanging out. And if not, have a good weekend. Enjoy.
Have a good weekend.
Okay, probably I should start with what I've been doing today since it's all in front of me. This is pretty cool. I got the whole lecture right in front. So I can scroll through, but you probably have some notes in front of you as well. I hope so. Any questions on anything I went over in class? Anything escape you? Didn't get it? Still don't get it? I'm just scrolling down through it slowly. Sort of a starting point, right? The main idea was to find what it means to be a linear transformation between two vector spaces. And had some defining properties, these two. Had these other properties, which are supposed to follow from the first two. Then I chose a simple example, a function going from R to R, and asked the question, which of those functions that go from R to R are linear transformations? And through class participation, we had a nice group effort here. We were able to figure out that if you're going from R to R, you better be, and you want to be a linear transformation, you really have to look like y equal mx. Or if you like, t of x would have to look like mx. Or m could be anything, any real number. Including 0, by the way. I didn't talk about that one. No, that's sort of a simple one. But if all vectors are sent to 0, that's also a linear transformation. Why? Well, you just got to figure out these two properties, right? So if everything gets sent to 0, the 0 equals 0 plus 0. Sure. And the 0 here, 0, again, there's some little confusion in this setup because in this case, the vectors are scalars as well. They're both the same. So you're really adding real number 0 to real number 0. The transformation, if that's 0, is equal to t of 0 is t of 0. And this is the first property you're going to prove in exercise 7. So that motivates proving these properties, because I'm claiming that the 0 function is a linear transformation. It makes this work. Does it make this work? Yeah, because if t sends everything to 0, this is 0. And if t sends everything to 0, this is 0. And you multiply 0 by a scalar, it's still 0. So that didn't come up before, but it came up now when I wrote this. T equals mx, m could even be 0. So that's even simpler than John's first example. John's first example was this line, which is the identity. But what I'm just talking about is the horizontal line through the origin, just the x-axis. That's a linear transformation as well. So going from R to R, now we didn't prove it, but we proved that anything that looks like this is the linear transformation. We didn't prove that every linear transformation looks like this, but they do. And then the next thing I assigned is what happens if you're going from R2 to R1, because that's what you know best from calc. Questions on anything in this lecture? Okay. Then what about questions about any homework problems? Old, new, orange or blue, doesn't matter what. If you don't give me one, I'll probably pick one of the current homework ones and just do it to get us rolling.
Could we do eight from section 1.6?
You have a question from 1.6? Sure. Let me get it. For that, let me get a new page. So let me flip the page here. Add something new. Oh, let me see. It's not letting me. Yeah, it did. Okay. So got a request from 1.6. Which one?
Number 8.
Number 8. Okay. Sure. Let's look at that. Number 8. Oh, yeah. That should keep us busy. Okay. Let me take a look at that again. Suppose W denotes the let W denote the subspace consisting of all vectors having coordinates that sum to 0. Okay. Excuse me. So this is 8 on page 55. And W look like coordinates in R5 consisting of all vectors having coordinates that sum to 0. So that would be things that look like A1, A2, A3, A4, and A5. Those are things in R5 where the sum of these add up to 0. That's what W is. Well, I should have said equals 0. Then it gives you 8 different vectors. The vectors generate W. So vectors U1, 2, 3, 4, 5, 6, 7, and 8. You're told that they generate W. So if you take all linear combinations of these 8 vectors, you'll get, that'll generate all the vectors in W. And that's just told you. And then what do they want? Find a subset of this set that's a basis for W. So that's the question. Let's call this set something. Maybe we'll call it G, since they generate everything in W. And what do they ask for? Find a subset of G that is a basis. Of W. Okay. So different ways to go about this. Let me see if it's obvious. So we're told that this is a subspace. So I guess we don't have to prove that. And we're told that these generate W, so we don't have to prove that. These are things we know. W is a subspace, and these generate W. Well, since W is a subspace, and it's a subspace of what, R5, What is the dimension? That would be a nice thing to know. What is the dimension of W? Well, every subspace would, the dimension of W would be less than or equal to the dimension of the whole space you're in, which is 5. The dimension of R5 is 5. And you could even imagine the standard basis vector there. Okay, so the dimension of W is 5 or less. Can we tighten up that number? If we can tighten up that number, then we can do what? We can find out how many vectors we need. And that would help us in figuring out what the basis of W coming from G would look like. Okay, I think I did some of this last time. I'm trying to remember. So let me just ask it directly. Do we know a basis of W that doesn't even depend upon the U's? Or do we know the dimension of W? So here's the question. That could be useful. I think last time, and I'm not sure if it was in your class or the other one, I think we tried to put together what a basis of W would look like. And let me play with that for a bit. So things in W have their coordinates adding up to 0. So something that looked like this might be a basis. So what am I doing? I'm looking for a basis of W. Now, that's not exactly what they're asking for, but it's similar and it's interesting in itself. So I think one vector in there that would work would be this: 1, -1, 0, 0, 0. Certainly that's a vector in W. Why? To be in W, the sum of the components have to be 0. And 1 plus -1 is 0 if you add all these. So that's in W. I think this would be another element of W. Okay. Well, it's easy to see it's an element of W. Why? Because the sum of the coordinates add up to 0. Would both of these be part of a basis? Are these linearly independent? I think so, because if you took A1 times the first one and added it to A2 times the second one, and if you set it equal to the 0 vector, what would have to be true? Well, A1 plus A2 would have to be 0. And minus A1 would have to be 0. And minus A2 would have to be 0. And the fact that these are both 0 means, and then the other ones Well, that would be enough. So that if these are both 0, that means this set is linearly independent. So this could be the start of a basis of W. Let's go a little further. What about 1, 0, 0, -1 here? Certainly that's in W. And what about 1, 0, 0, 0, -1? All of these are in W. Are they all linearly independent? I don't know. Let's check that real quickly. So if you set this equal to the 0 vector, I'm trying to see if all the A's would have to be 0. If they all have to be 0, then that would mean these vectors are linearly independent. Let's see. So the first vector here, or the first component here, would be A1 plus A2 plus A3 plus A4. Okay. The second component would be minus A1, 0 from here, 0 from here, 0 from here. The third component would be 0 from here, minus A2 from this one, minus A3, or 0 from this one, and 0 from this one. And then the last component would be 0 from the left, 0 here, 0 here, 0 here, and minus A4. So this means A1, A2, and A4 are 0. And if you put those into here, that means A1 is 0. So A1, A2, A3, A4 are 0. So that means what? These are linearly independent. Okay. So what does that tell me? That tells me the dimension of W is at least 4. Because if you could find 4 linearly independent vectors in the subspace, then the basis is at least 4. But W is in R5, and W doesn't contain everything. I mean, it's easy to come up with a vector, a simple vector like all ones. Is not in W, because by definition, if you add them all up, you don't get 0. So W doesn't have all of R5 in it, but it has at least 4 vectors. So I'm saying the dimension of W is 4. Okay, that's helpful. It's not exactly what the problem was asking for, but it's sort of something that's interesting in itself. And look how I came up with the basis. I think I came up with this the other day, but perhaps didn't have time to develop it. Any questions thus far? Once I know the dimension of W is 4, then I can go back to the original problem. The original problem was to find vectors in G that generate W. But now I know the dimension that I'm looking for 4 vectors that do that. Why? If I have more than 4, if I have like 5, 6, then they won't all be linearly independent, because the biggest linearly independent set here will be 4, because I've already decided this is a basis. So what am I trying to do? I'm trying to figure out 4 of the vectors in this collection of 8 to keep and form a basis from. And that will generate all of W, which is what we're trying to do. Find a set G that's a basis. So we already know this generates all of W. So there's some extra ones that are unneeded. And I'm looking for the 4 independent ones of these that would generate, that would form the basis, basically. Okay, so what's an efficient way to do that? Maybe we can start just by looking at some of those vectors and seeing that some of them are linear combinations of others. So I haven't done that yet. So the plan is looking at all these 8 vectors and try to reduce them to a set of 4. Why? Because I already know that the basis of W has dimension 4, has 4 vectors in it. So if I'm trying to get a basis out of this set, they already generate. So that part is half of being a basis. I just have to throw away 4 of the vectors that can be constructed from the other 4. There may be different ways to do that, by the way. I mean, one person's answer may not be equal to another. So, I mean, somebody might pick the first 4 and maybe someone else would pick the last 4. I don't know. Let's see how to go for it. Any questions thus far, though? Okay, so let me look at the vectors. $45. Oh. $55. Okay. So the vectors look like this. If I mess one up, please let me know. So keep me honest. Okay. So U2 looks like everything in here is 3 times something. So I can factor the 3 out. That would leave me -2, 3, -4, 5, and -2. So that's just something I noticed. They all have a common factor of 3. But now that we've noticed that, notice this thing, it looks like this. The underlined portion is almost the same except for the negative sign, right? So what does that mean? It means that U2 is just -3 times U1. Is that right? I think so. Yeah. So just an observation. U2 is -3 times U1. And that came about by noticing that these all had a common factor of 3. So what does that mean? That means I don't need both of these vectors in my collection, because if I have U1, then I can create U2 by taking a scalar multiple of it. So I'm going to throw out U2 and keep U1 so far. Okay, so I'm throwing out vectors that I could create from the other vectors, because we already know this generates the whole space. So to form a basis, if I can generate every vector in here, then I'll be able to generate everything in the whole space W. So I'm just looking for sort of a set that's all independent, and I can see that U2 and U1 were not independent. Now maybe I can do the same trick elsewhere. So for example, 2 is a common factor here. So it looks like we could factor the 2 out, leaving 1, -4, 1, -1, and 3. Is that right? I believe. To be honest. And okay. And I guess there's some other things I can factor out. So from this one, I can factor out a common factor of 3. And so I'm trying to use the same kind of observation that I used to get rid of U2. So 3 coming out would be what? 0, -1, -6, 3, and what? 4. Okay, so each of these 3 vectors have a sort of a simpler form. Let's look and see if that occurs elsewhere. So if I want, okay, if you see something, I'm happy to take any help. So if you see some other way to get some of these other vectors from the ones we already have, I will certainly take some assistance. I'm looking. So I think it would be easier. Well, this one I've already thrown away. So I've thrown away U2, right? So I might as well. Yeah, might as well just delete it. So we're down to 7. So if we want, let's just continue to look a little bit. With these 7, do you see any relationship between the 7? So can you see something times 1 plus something times another equaling one of the other ones? That's sort of what we're looking for. And probably it'd be easier to look at it with these in mind rather than these. So let's see. But I think I have a plan now, other than doing it this way. So give me a second more. Well, okay, I have two different ideas of how to go. One is a little lengthy, one is a little shorter, if it works. Let's do the longer one for now, just to see where it leads. So, but before I do, let's give it another 30 seconds. Does anyone see any relationship between these 7? There probably is one. So if you add 2 of them, you get a third one, that kind of thing. So for example, suppose you added U4 and U5 and U7. If you added these together, you would get 0, you would get 1, you would get -1, you would get 4, and you would get -5. Make sure I did that right. Yeah, do you see this anywhere here? Well, 0 is here, but -1 is there. I don't see how you get these things from that. Okay. Yeah, I'm getting lost in there a little bit. Let's just do it the long way. Okay, so the long way would be what? We know that they're dependent, so let's find the dependence. So there would be so if we have 0, 0, 0, 0, 0. Let's write it as A1 times this. Okay, so I've written a linear combination of these. Make sure I did it properly. If I miss a minus sign, that's a key problem. So hopefully everything is here. I think they're all there. So writing out the equations, what would you get? You get 0 equaling 2a from this 2a1, and then 3a2, and plus a3, minus a4, 0, plus a6, plus 2a7. That's the first equation. The second one would be what? There's 5. So minus 3a1. Minus 2a2. Minus 4a3. Plus a4. Minus a5. 0. And minus a7. Third equation. 4a1. What? 7a2. a3. 2A4 minus 6A5 minus 3A6 and plus A7. Make sure I did that right. 4A1, 7A2, plus A3, 2A4, minus 6A5, minus 3A6, plus A7. Looks fine. Okay. 2 more to go, I guess. Minus 5A1. Minus 9A2. Minus A3. Plus A4. Plus 3A5. Plus 3A6. And minus 9A7. And last, 2A1 and A2, 3A3, minus 4A4, 4A5, minus 2A6, and 7A7. Call this system 1. Try to get rid of some zeros. Let's see how to do that. Different ways to go. I'm trying to survey it and just see what's the easiest way to proceed. Since we already have A2 alone here, that might be an easier way to go rather than working with this. Yeah, why don't we try that? So let's subtract 3 times this row from the first one. So when I do that, when I subtract 3 times A2 from this, I'll get 0 up in here. 3 times this from this would be 6A1, and then subtract it from this. So that would be what? 2A2 minus 6A1, so it would be minus 4A1. 3 times this and subtracting it, that seems correct. 3 times this and subtracting it from this, that's 1 minus 9, which would be minus 8. 3 times this, which would be 12, and subtract, which means add, it would be 12 minus this, so it looks like 11. 3 times this subtracted from this would be minus 12, 5. 3 times this would be minus 6, subtracted from that would be 7. And 3 times this, which is 21, subtracted from this would leave me with what? Minus 19. Okay, so there's a line here. Check those, make sure I did it properly, but I think it's okay. So I'm subtracting this equation times 3 times the first. I guess I should check it myself. 2 and multiplied by 3 and subtract. So this would be -4, this would be 0, this would be -8, this would be 11, this would be -12, that's correct. 3 times this. Yep, and then 3 times this. Yeah, I think so. Okay, now what? Similar kind of stuff for the next ones. Multiply this row by 2 and add it to the second row. So we do that. 2 times this would be 4. Added to this would just give us an A1 for the second equation. 2 times this and add it would give us 0. 2 times this and add it would be 6. -4 would be 2. 2 times this and add it would be -8. Added to this would be what? -7. 2 times this would be 8. And added to this would just be 7. 2 times this and add it would be -4. And 2 times this and add it would be 14. -1 would be 13. Is 7. Okay. 2 zeros introduced here. I guess here we would be multiplying by 7 and subtracting. So 7 times this is 14. Subtract that from this would be -10. Seven times this and subtract would give you 0. 7 times this is 21 and subtract that from this would give us -20. 7 times this and subtract from this, 7 times 4 is 28, -28. And then we're subtracting, right? Yes. The -28, so it'd be -26. 7 times this and subtracting, that's 28. Subtracting from this, 26 and 28 is what, 34? Yeah. Seven times this, which is -14, then subtract that, so that'd be 14 minus 3, which is 11. And 7 times this, which is 49, and subtract that from this would be what, 50? Okay. Again, I suggest somebody check those. I could easily mess up a sign. What's next? We've got the first 3 with zeros, and now we're doing what? 9 times this and adding it to that. 18 and -5 is what? 13? And -5 is 13, yes. There's multiplying by 9 and adding. So this would be 9, and this would give us 0. 9 times this is 27. Take away 1, 26. 9 times this is 36 with a negative, and minus 35. 9 times this is 36, and 3 more is 39. Nine times this is 8 minus 18. And we're just adding this to this, so that would be minus 15. 9 times this is 63. 63, and we're adding it to this. So what do you get? 54. Again, keep me honest. 9 times 7 is 63. 63, take away 9 is 54. That seems okay. Okay. And then the last one is just this one again.